Why NumPy? Throughout this section, we're going to explore this popular library called NumPy, which are very similar to Python lists. It's one of the most used and popular libraries when it comes to data science and machine learning. But I want to ask you, why do we need this? Don't we have Python lists? Why is NumPy so popular and a must-use tool for machine learning? There are two main reasons why we want to use NumPy for our problems. You see, under the hood, many functionalities that NumPy offers us are actually written in C, a programming language that is really, really fast. If we used Python lists, it would actually be a lot slower to do some of the things that we're about to do. So NumPy operations on arrays and lists are a lot faster than performing the same operations in Python. And as you'll find out, when it comes to machine learning, we do a lot of computation. We do a lot of processing. And that's why GPUs, or graphical processing units, are used, because so many calculations need to happen. So we need to have any possible performance advantage we can, which NumPy offers. The second reason we want to use something like NumPy is that when it comes to machine learning, well, machines usually only understand ones and zeros. And things like numbers, which can be contained in NumPy, are really easy for machines to understand versus something more complicated. For example, an image can be represented in numbers, where a number represents the color of a pixel. And we'll see later on in the course where we try and convert different fields, different attributes into numbers. For example, if a patient has heart disease, instead of yes or no, we convert it to 1 or 0. This idea of converting data into something that a machine can understand, like numbers, like binary, like ones and zero, allows us to make machines learn. That's how machines learn. Machines learn by performing multiple operations. And by storing this information in an array like NumPy is a great way for us to represent that data from what humans can understand to what computers can understand. But you'll see that as we progress more and more through the course. For now, let's get started.
Welcome back. In this section, we're going to look at NumPy. And now I'm very excited about this section because NumPy is basically the backbone of all data science, machine learning, and numerical computing in Python. And that's actually what NumPy stands for. It stands for Numerical Python. And what is NumPy? Well, in all of machine learning, no matter what kind of data that you're working with, now this could be a data frame like we saw in the previous section on pandas, NumPy is going to form the foundation of turning your data into a series of numbers. And then what a machine learning algorithm will do is work out the patterns in those numbers. So if we refer back to our machine learning modeling framework, we've got step 1 is problem definition, step 2 is data, evaluation, features, modeling, and experiments. And then if we have a look at what tools we can use, in this section, we're going to be focused on NumPy. NumPy comes into the data analysis section. However, as you'll see in the future and what we just referenced before, is that machine learning, although it's referred to as modeling, is essentially taking data, turning it into numbers, and in this case with NumPy, usually the form of a NumPy array, which we'll have plenty of experience with after this section, and then finding patterns in those numbers. So almost across this entire pipeline, NumPy will come into play. Now, why NumPy? Well, the main reason we use NumPy instead of pure Python, I mean, you can do numerical calculations in Python, but usually if we want to do large-scale numerical calculations, we refer to NumPy. It's because it's fast. And now, the reason why it's fast is because behind the scenes, there's optimizations written in C code. The beautiful thing about the NumPy package is that you can use these C code optimizations using pure Python. That means you don't have to know C to be able to use NumPy. And Python is a bit easier to write than pure C, so that's the advantage of using NumPy. Now it gets these optimizations in speed through a process called vectorization via a term NumPy uses called broadcasting, which is essentially just avoiding writing loops when you're writing calculations. Because if you're writing loops to make calculations, such as in Python to calculate over a list, that can form some eventual slowdowns if you have a list, say, of millions of different numbers, which becomes common practice when we're working on machine learning projects. And as we mentioned before, NumPy is the backbone of other Python scientific packages. NumPy actually forms the basis of the pandas package. So what are we going to cover in this section? Well, of course, we're always going to be focused on the most useful functions, the ones that you can start using straight away. We'll have a look at different NumPy data types and attributes of those data types. Now, the main one is an ND array, but we'll have a look at that in another video. We'll look at how to create arrays. Arrays you can think of as a list of numbers. We'll have a look at how to view arrays and matrices. Now, a matrix or a matrice you can imagine as a combination of different arrays. We'll then look at how to manipulate and compare arrays. We'll then finish up with sorting arrays, which is sorting out different lists of numbers. And then some practical use cases of where arrays get used or where NumPy can be used to turn data into lists of numbers. So, where can you get help if you get stuck? Well, the steps you want to try and follow is to follow along with the code. So as we're going through the video, as we're working through our Jupyter Notebook, through the introduction to NumPy lessons, you want to follow along as best you can. Now, if you can't keep pace or if I'm going too fast, that's all right. Feel free to stop it, go back, practice something on your own, but you should be practicing writing the code and running it as much as possible. So that's step 2, try it for yourself, try to run the code. Remember the saying, if in doubt, run the code. If you get stuck on a certain function or a certain thing that we've covered, you can try to search for it. Here you'll probably come across Stack Overflow or the official NumPy documentation. Then after that, once you've searched for it, if you find something on Stack Overflow or the NumPy documentation, the important thing is to keep trying again. Enter the code that you find in the Jupyter Notebook, practice running it. If in doubt, run the code. And then finally, if you're still stuck, don't forget, you can always ask for help. There's no such thing as a stupid question, because if you have a question, it's likely someone else has the same question. You can ask on Stack Overflow or on any other resource you can find. All right, with that being said, that's an introduction of NumPy. It's the foundation, it's the backbone of other data science and scientific packages, but let's get in code. Let's see what it's all about. All right, now we've had a little bit of a conceptual overview of NumPy. Let's get hands-on and start to write some NumPy code. So I'm going to follow the little workflow that we've kind of set up over the past few lessons and sections. Start off in a terminal, and I'm going to change directory into this little folder that I've got on my desktop. Yours may be stored somewhere else. So cd/ml course. Now I've got a folder in here called sample project, which has my environment. You'll want to change into the same folder that contains your environment. Hit enter. Now we're in the sample project folder. Beautiful. And we're going to check using conda env-list where our environments are. So I can see I've got one here. I've got a few. Currently base is activated because I've got the star, but I want this one because that's in my sample project folder. So we're going to type it out. You could copy this and do conda activate this here, but we're in the practice of writing things for ourselves because I want to get as used to as possible, writing as much code as possible. ML course, sample project. Now remember, you'll want to change yours to wherever your environment folder is stored. Activate. The first thing we notice is that this has changed from base to our active environment. And now the next step is to create a Jupyter Notebook, our favorite workspace tool. Let's load that up. Now this will open our browser. We brought to the Jupyter dashboard. It's nice and zoomed in. Excellent. We've got our folders here and files that are within our sample project folder. Yours may be a little bit different, but we can see, in my case, I've got the introduction to pandas notebook, the example notebook from before, my environment folder. We're not worried about these. We're going to start a new notebook, Python 3. First thing we're going to do is rename it to Introduction to NumPy, because that's what we're working on. Hit enter. And we'll save that. When we come back to the dashboard, we've now got Introduction to NumPy running. Beautiful. Now the first step for using NumPy is to import it. Import NumPy as NP. Now NP is just short for NumPy. If you see this abbreviation somewhere, you can probably safely assume that it's referring to NumPy. It's just to prevent us from having to type out NumPy every single time we want to use a command. We'll hit Shift and Enter. Beautiful. Now, in this section, we're going to be focused on NumPy's data type and attributes. So that's what we'll create a little heading because we are in the business of making attractive and communicative notebooks. Data types and attributes. We'll hit Escape and M to turn it into a markdown cell. Wonderful. Data types and attributes. Now, data types as a plural is kind of a lie because NumPy main data type is ND array. It's only really got one data type, so everything you see in NumPy is likely an ND array, and this stands for n-dimensional array. And an array can be almost any list of numbers you can imagine. And n dimensions means the list of numbers could be almost any shape that you can imagine. But rather than talk about it, let's create it. So A1 for array 1, we'll create a sample array. Now you can do that by going numpy.array, which just means access the array function from NumPy, which we've imported as NP. And to build an array, which is a list of numbers, we want to pass it a list of numbers. So let's do that. And then to see it, we'll type it again, Shift and Enter. Excellent. We've got our first NumPy array. Now this is exciting. Let's check the type of it. NumPy.nd array. Wonderful. So that's the same as here. Remember, this is just n-dimensional array. Now, for some more examples, let's create a few more arrays. NP array. We'll type out this one. This will have 2 brackets. We'll see why in a second. Now we'll separate it. We'll go to another line. 1, 2, 3, 4, 5. Actually, let's make this 6.5 and this 3.3. So we've got some floats as well as integers inside NumPy. And there we go. We might make another one called A3 NP array. And this one we might actually do 3 brackets. So we're getting a bit adventurous here. We'll make this 1, 2, 3. Let's go all the way up to 18. Bear with me. Type along if you can. 5, 6. And then we'll go 7, 8. We want to make sure it looks all right. 9. And then we'll leave 2 brackets here. Or actually, yeah, 2 brackets. That's correct. I'm just counting the number of brackets. You'll see why this is important in a moment. We're just typing out the numbers from 1 to 18 in a very kind of cryptic format at the moment. 13, 14, 15. We've got a little bit more. 16, 17, 18. My goodness. We made it in the end. Let's see if this cell runs. Beautiful. If in doubt, run the code. Now, why would we do that? Well, let's have a look at these 2 arrays. A2. There we go. We can see that. We've got 2 sets of brackets here. And we've got 2 more here. Now let's have a look at A3. Ah, okay. Now this one, it's kind of come out the exact same way as we've got here. Now before we get any further and check out some of the attributes that these arrays have built in, let's have a look at the anatomy of an array. So this is the anatomy of a NumPy array. This is A1, the one that we've just created. This is A2, and this is A3. There's a reason why I put in these numbers here, so we can exemplify the kinds of shapes of different arrays. Now this is very important in machine learning because oftentimes with a machine learning algorithm, your main focus will be making sure the shape of your data that goes into a machine learning algorithm lines up with the other data that you're putting in as well as the output. But we'll see that in future sections. This is just learning the shape of different NumPy arrays. So we've got 1 here, so there's 1 row and 3 columns. So this would be shape 1, 3. Now this kind of data here is referred to as an array or vector. A vector is just a one-dimensional array. If we go to this next one, which is A2, we've got 2 rows and 3 columns. So this one has the shape 2, 3. It's more than one dimension, and can be referred to as a matrix. So if you hear something referred to as a matrix, it's probably got more than one dimension. So see how a vector is just one row? This matrix has 2 rows. Then if we go down to A3, we're starting to get 3-dimensional here because we've got the axis going back here. This is where the n in n-dimensional array comes from. Now, it's very hard for us humans to visualize anything more than 3 dimensions, but in NumPy and with computers, you could have as many n's as you want. So this could go up to 4, up to 5, up to 6, up to 7. Depending on what type of data you're working with, you may have thousands of different dimensions. But if you hear axis 0, it's usually referring to rows. Axis 1 is usually referring to columns. And then axis n is usually referring to dimensions that are beyond just rows and columns. So this array here, or A3, would have the shape 2, 3, 3, because there's 2 rows, 3 columns, and we've got 3 across here. So that's the final one here. And now, if n was higher, there might be more commas and this little shape would extend out here. Okay, so now we've got the anatomy of a NumPy array down pat. Don't worry, you can take a screenshot of this if you like, otherwise it'll be in the resources section. Let's have a look at some of the attributes associated with NumPy arrays. So the first one we'll take a look at is a1.shape. So it's 3, something. Now this is blank. Now the way NumPy kind of formats this data is that although we've said that the shape is 1, 3, NumPy kind of stores it without the row at all. So it's just got the 3 numbers here. That's just a little tidbit of how NumPy displays some kind of shapes. But if we have a look at the shape of A2, we can see that it's the same as what we've used in our anatomy of a NumPy array. And then if we go the same for A3, 2, 3, 3. Okay, let's have a look at a few more. So if we go a1.ndim, which is short for number of dimensions, maybe we do a2.ndim and a3.ndim. And what putting the comma here will do is when the code comes out, it'll just print it with commas spacing the 3 different variables apart. So this is number of dimensions. So A1, let's have a look at it again. A1 has a dimension of 1. We'll have a look at A2. Has a dimension of 2. And A3 has 3 dimensions. And so this is where the ND array data type comes in, is that these dimensions, depending on how complex your data is, could just keep going. And now the whole premise here, as we'll see some practical examples in the next couple of videos, is that whatever data you're working with, it somehow gets turned into numbers, and then a machine learning algorithm will find patterns in these numbers. Now, depending on what data you're working with will depend on how many dimensions there are. But let's not stop there. Let's have a look at the D-type attribute. You might be able to guess what data type these are. Let's go here. Shift, enter. So we can see in our A1 array, we've got ints. In our A2, we've got floats as well as ints, but it's going to default to float because there can only be one kind of data type. So it will automatically just turn the rest of the numbers in here into floats. And A3 is also just integers. We got a couple more. A1 size, A2 size, A3 size. We've got 3 elements in A1, we've got 6 elements in A2, and we've got 18 elements in A3. Now if we have a look at A3, that makes sense. Beautiful. So the size attribute tells us how many elements we've got total in our array. Now, we've got one last one, which is type A2, type A3. I think we've already seen this, but I'm going to get you to guess what it is before we hit shift and enter. 3, 2, 1. These are all ND arrays. So although they vary in size and shape, A1, A2, and A3 are all of the type ND array. Now this is an important concept to remember. No matter what type or what shape your NumPy array is, all of the functions and different data manipulations that you see throughout this section, if it's in a NumPy array, if your data is in an ND array data type, all of the things we're about to go through can be used on that. So that's a very important point to remember, is that the ND array is a universal data type, and it's very, very flexible. So now, to really exemplify NumPy being the backbone of other scientific data packages, that is, let's put a note here, create a data frame from NumPy array. So let's have a look. First, we'll import pandas as PD. Beautiful. And then we might create one from our existing array. So pd.dataframe. We're just going to pass it A2. Let's have a quick look at what A2 is. A2. Wonderful. So there's A2. Now let's see what that looks like. Oh, we need to view it. Shift and enter. There we go. So this is a pandas data frame, and this is our NumPy array. So essentially, no matter what's in our pandas data frame, if it's all numbers, pandas is built on top of NumPy. So to represent our data as a data frame, it's just combining NumPy arrays in a formatted way. So that's a very important point to remember as well, is that once we start to get into the weeds of NumPy and start to work out what kind of numerical computing it can do, we can start to think, okay, so if we have some data and we import it in pandas, it's actually just a different combination of NumPy arrays. So if we want to perform some manipulations on it, we're actually just performing manipulations on different lists of numbers. All right, that's a brief introduction to NumPy's main data type. That's the main thing to take away from this, is that ND array, whatever array you have in NumPy, is of type ND array, and that pandas and other machine learning algorithm packages are built on top of NumPy, and machine learning is finding patterns in NumPy arrays. So with that being said, let's take a little break if you need to, go back and explore, create an array of your own by trialing it out. If in doubt, run the code, and I'll see you in the next video. Welcome back. Hopefully you've had a little bit of a play around with creating your own NumPy arrays, but if not, that's okay, because in this section, what we're going to do now is have a look at how we can create NumPy arrays. And so in the previous section or video, we went through creating some of our own arrays, A2, A3, A1, and we learned about different attributes that these arrays had, but it was very tedious typing out all of these different numbers. So let's have a look at some easier ways. First, to begin with, we'll just see it again, just in case. So sample array, how we did it the first time. mp.array, and we passed it a list of numbers. Wonderful. Oh, we'll go here, and just so it prints out, we'll have sample array here. So this is going to give us a one-dimensional NumPy array with the elements 1, 2, and 3 in it. So if we check this array's data type, there we go. Beautiful. Okay, now, for example, what if we wanted to create a NumPy array that was already filled for us? What if we didn't want to pass anything here? Let's have a look at how you could do that. Let's make one called ones, and you go mp1s. Actually, what does np.ones? What do you think that will be? Well, I've got a little trick I can show you to get a little preview of this. Let's hit Shift and Tab whilst we're inside the brackets. Oh, what have we got here? Signature np.ones shape docstring. Return a new array of given shape and type filled with ones. Beautiful. So what Shift and Tab does, remember we'll exit out of here, we'll come back into this. If we type in any kind of function, so np dot something brackets, if we push Shift and Tab while we're inside here, what that's going to tell Jupyter to do is open up the function's docstring. So this gives us information. So this information here comes straight from the NumPy documentation. This is going to tell us what this function does. Return a new array of given shape and type filled with ones. Let's see here, parameters shape, int or sequence of ints, e.g. 2, 3. Let's use that example, 2, 3. Shift and enter. Okay, what does this look like? Ones. Ah, an array filled with ones. That's exactly what it said. Shift and Tab, return a new array of given shape and type filled with ones. Now we haven't put in type here, but we have given it shape. Okay, let's have a look here. Ones.dtype. That's dtype float. So if we use ones, pretty sure float is the default data type. Now you could probably find that. That's a little challenge for you, is to find out what the default data type is by reading through the docstring. Let's keep going. If we checked type of ones, we can see that it's our beautiful and favorite data type is ND array. Wonderful. Now let's have a look. What if we wanted another array, but not with ones, we wanted one with zeros? MP, let's see, MP zeros. Does it have this? Docstring, return a new array of given shape and type filled with zeros. Okay, let's do the same again. NP.zeros, zeros. Wonderful. Okay. Now you might be thinking, Daniel, why would you want ones? Why would you want zeros? Well, in that case, you could imagine zeros as kind of like a placeholder array. Maybe in machine learning, you want to fill an array with some initial data or that data you don't know yet. So you create the zeros just to work out the shapes of data you're working with. So before you even implement any data, you could make sure that your shapes lined up by using arrays filled with zeros. But let's keep going. Let's see how we could make a few more different kinds of arrays. Let's go range array equals np.arange. Let's see, shift and tab. That's what we're practicing at the moment. Return evenly spaced values within a given interval. Start, stop, step. Okay, let's have a look. Start number, stop number, step number. Well, let's try it. If in doubt, always try. 0, 10, 2. Now, if this is going to be start, stop, step, what do we think that this will return? Let's have a look. Range array. So it's going to start at 0, 0. It's going to stop at 10, but it's going to step up by 2. 0, 2, 4, 6, 8. Wonderful. Let's keep pushing forward. Let's go random array. What if we didn't know what numbers? We just want NumPy to just fill an array full of random information for us. np.random. Let's do rand int. Shift and tab. Let's practice. Docstring. Rand. Low, high, size. Return random integers from low to high. Exclusive. Okay, return integers from the discrete uniform distribution of the specified d-type parameters. Low, int or array of ints. High, int or array like of ints, optional. Size. Okay, so let's go 0, 10, size 3 by 5. What do you think this will return? Let's have a look. Random array. Size is not defined. What have we done wrong here? We haven't set size equal. Wonderful. So what this has done, we will see what the actual docstring. Return random integers from low, this is our low, 0, low, inclusive to high, exclusive, 10, of size 3 by 5. So now, if we go random array dot size, we have 15, and we want random array dot shape 3, 5. Wonderful. And we can see that in our array, the low is 0 and the high is 10. Wonderful. Let's see one more way of creating random arrays. Random.random. NumPy has a fair few different ways of creating random arrays. You don't need to know them all. There we go. So random.random, what does this do? Shift tab. Return random floats in the half open interval 0, 1. So this is going to return, and it takes a parameter size. Let's save this to random array 2. And then we want to show it, random array 2. Wonderful. Random array 2. Let's check the shape. Shape, there we go. Shape is 5 and 3. Wonderful. So that means it's always rows, then columns. So 5 rows, 3 columns. 1, 2, 3, 4, 5. 3 columns. And if we check this, it's going to be between the intervals 0 and 1. Wonderful. Got a random array. And let's see one more. So we want random array 3. Now this is where NumPy can get a bit confusing, is that these dot rand or random and dot random 5, 3 do very similar things. Random. We go Shift Tab. We can see what the docstring says here. Return values in a given shape. So that's what I've done, passed D0 and D1. So dimension 0 is 5 and dimension 1 is 3. So remember, always goes dimension 0, dimension 1. If we go back to the anatomy of our NumPy array, axis 0 is the same as dimension 0, which is the row here, and axis 1 is the same as dimension 1, which is the columns here. Wonderful. Now, the thing you should know about the random numbers in NumPy is they aren't actually random. They're set with something called a random seed. NumPy.random seed. What could this mean? They're pseudo-random numbers. Pseudo-random numbers. We'll have a look at this in the next video, but this is an important concept to remember going forward, is that when NumPy generates random numbers, they're actually pseudo-random numbers. So take a quick break, try practice creating some of your own random arrays using the .random or randint. Have a look at the docstrings by pressing Shift Tab, and then in the next video, we'll have a look at np.random seed and see how we can generate some non-random random numbers. Welcome back. In the last video, we saw a few different ways that we can create NumPy arrays. So we've got a sample array, which could really just be a simple array by we're using np.array, passing it a list of numbers. There's another one if we wanted to create an np array of just ones, we can pass it a shape. And if we keep going, if we want an array of zeros, we can use np.zeros. If we wanted an array that's between a range of different numbers, say starts at 0, stops at 10, steps at 2, we can use arange. And if we wanted an array of random numbers, we've got a few options. We have randint for returning integers between a certain range, or we have random.random for returning numbers between 0 and 1 of a certain shape. And how do we know what these functions do? Well, we can press Shift and Tab, and that's going to return the docstring. So here we can see np.random.random, return random floats in the half-open interval 0 to 1, and it takes a parameter called size, which in our case we've done 5 and 3. So 5 rows, 3 columns. We can see that there. Wonderful. Now we also said in the previous video that NumPy generating random numbers, they aren't actually random, but you might be running this cell. I've run this one about 50 odd times, and each time new random numbers have come up. So what's the deal? What gives, Daniel? Why I think these numbers are random? Well, you'd be right, they look random to us, but what they really are is pseudo-random numbers. And we can see this by using NumPy random.seed. Now, throughout your machine learning endeavors, you might see this little function at the start of a notebook or somewhere along the lines, wherever NumPy's random package is being used. Now, what does this do? Now, rather than talk about it, we're going to see what it does in a practical sense. So let's just comment this out for the time being. And we'll just create another one. We go random array 4, just so we can make sure it's not the same as this one as before. np.random.rand. Let's go randint. We want numbers up to 10 of size 5, 3. Wonderful. And then we'll have a look at what this looks like. Random array 4. There we go. Okay, numbers. These are between 0 and 10. We've got 0, 5. Beautiful. Of size. Well, this is really shape. That's a bit confusing with NumPy's. Is that the size parameter of this creating array function is actually the shape attribute. But that's all right. We can figure these things out. We're smart enough to do that. But every time if we ran this, we're going to get what seems to be a new random array. And for what we're looking at, we can consider this random numbers every time. But what if we wanted to share our notebook with someone else? And we wanted them to run our cells across the notebook, go through from top to bottom, and get exactly the same results as what we did so we can reproduce our experiments. Well, that's when NumPy's random seed comes in. It allows us to still generate random numbers, but random numbers that are reproducible. So let's have a look. If we set random seed at the top of this cell to be 0, so we can go Shift Tab, takes a parameter, seed equals something. So we can actually set this to any number we want. We'll have a look at that in a second. So in this case, we'll set it to 0. We'll hit Shift and Enter. What's happened? 50. Hold on. The numbers they've stopped changing on us. Now what if we comment this out? They've changed. Okay. So what the random seed function does is it essentially says, hey NumPy, I want you to create random numbers, but keep them aligned with the seed. So random seed is 0. We're always going to see this combination, 503, 503, 503. I'm running this cell. We can see the numbers going up here. Now, this works no matter what your seed is. So 637, 637. We could even set it to 9999, 031, 031. Huh. Now, let's try again with another random function. That was randint. Maybe we go here. Let's go random array 5 just to make sure that it's different. np.random.random and shift tab. What does this take? Size equals something. So we want 5 and 3 again. Be out of view. What's going on here? Random array 5. Okay, every time we run this, new numbers. Okay. Now let's put a random seed in here. What should we do? What number are you thinking of? I'm thinking of 7. There we go. 7. Ah, the numbers still seem seemingly random to me. But what the random seed does is, remember, it says to NumPy, hey, generate some random numbers, but if you see the random seed and it's set to 7, make sure they're same every time the random seed is set to 7. So now if we run this exact same code in the next cell, random array 5 equals np.random.random 5 3. And we want to see it again, np array 5, different here. If we kept going with this, we would eventually line up with the random seed, but we don't have time to do that. So what's the takeaway here? Well, the numbers that you see NumPy generate, seemingly random, but they're not actually random. They're pseudo-random numbers. So whenever we run this function without a NumPy seed being run, what it's actually doing is setting the seed to be something random every single time you run this. But if we set our seed manually, we're going to get the same random numbers back. Now, the important takeaway is that these numbers are seemingly random, but the main purpose of using random seed is if we wanted someone else to be able to use our notebook and generate random numbers, but the same random numbers as us, and thus reproduce our experiment exactly, we would set a random seed. So if you see np random seed, that's what it's doing. It's making sure the random numbers in the cell that it's being run are the same every single time. Okay, now we've seen that. We've seen how to create some arrays. We've seen how to generate arrays with random numbers. Let's look at how we can view different arrays and matrices. So take a little break, try to generate some more random arrays, practice around with NumPy random seed, and I'll see you in the next video. Welcome back. In the last video, we had a look at NumPy's random number generator and how it's random, but we can use NumPy's random seed method to make it not so random and create pseudo-random numbers. Now we're going to have a look at different ways of viewing arrays and matrices. There we go. Shift and Enter. Remember, we're making markdown cells so that our notebooks are beautifully formatted. And actually, before we jump into that, how do you think we'd find the unique numbers in these arrays? Maybe this one is a bit better because that's got integers. These are all floats here and they're way too long. But how would we find the unique numbers in random array 4? Let's have a practice of how we might do that. So we'll open up a tab and we'll go how to find unique elements in a NumPy array. Beautiful, that's pre-filled. So it's going to take us to the documentation. NumPy.unique, find the unique elements of an array. Wonderful, that's what we're after. So if we go down in the documentation, you'll see down the bottom there's examples. Now, this is what we're after. This is the process you can go through. Say someone came to us and was like, hey, you've got your random array 4. I need the unique numbers from that. So we'd find the documentation, we'd come to the example section, or we'd just read it to see if it does what we need. Then we'd have a look down here. So they've got an array A, MP unique A array. It shows the unique numbers there. Well, let's have a look. Let's practice. mp.unique, and remember, if we hit Shift and Tab, we've got information here. Find the unique elements of an array. Wonderful, that's what we're after. So we're going to pass it random array 4. Random array 4. Shift and Enter. And what this has given us is 0, 1, 3, 4, 5, 6, 8, 9. If we come up here, and that is because we created random array 4 using randint, passed it 10, so that means it'll use the numbers between 0 and 9 of size 5 and 3. So we can see the uniques, we haven't quite got all the numbers between 0 and 9. We're missing 2, we're missing 7. Beautiful. But that's just a quick little tidbit of how you might find a function using NumPy. You might come across the documentation. Stack Overflow is another resource that you'll often come across, but that's the steps you'll take. Now let's get into section 3, viewing arrays and matrices. So we've got our arrays A1, A2, we created these earlier, A3. Now viewing arrays and matrices takes a bit of practice, and creating them of course too, but if what you're seeing in this section, how to view them, is a little bit confusing to start, don't worry, I still get confused. The important point is to start practicing. So if we wanted to see element 0 in A1, we could use 0 indexing. So let's try that. Beautiful. Let's go the same for A2. Wonderful. Now this is going to give us this first row here. Why is that? Well, if we go above here, A2.shape. Okay, so it's got 2 rows. So that makes sense. We're indexing into the first element of the shape. Now let's try A3. A3.shape. This is 2, 3, 3. Let's get A3, 0. Wonderful. But if we have a look at all of A3, so it's giving us back the first row. So if we see here 2, 3, 3, and A3, 0 is giving us back this first matrix or first array. Now remember the anatomy of our arrays and matrices. Although this is still a NumPy array, it can be referred to as a matrix. This is where some of the terminology gets a bit confusing. Usually a one-dimensional array is referred to as a vector, but anything more than one-dimensional is referred to as a matrix, but is also of type array. So that's the important thing to take away, is that an array is still this, but anything with more than one dimension is a matrix. Let's have a look at some more indexing. So we go A2, maybe if we wanted index 1. So we'll have a look at our array again. Index 1, what will this give us, do you think? Shift and Enter. So it's given us position 1. So let's try again. Let's do a bit more of a complicated one. We can use slicing with arrays too, which is beautiful, just like Python lists. Maybe we want the first 2 values of A3. So we want the first 2 values of each row, column, and array. So let's try that. First 2 values of each shape. What do you think this will give? So let's have a look. So we got the first 2. And the second 2, which is 1, 2, 4, 5, so it's this section. And then we got the final 2, which is 10, 11, 13, 14. Beautiful. Now remember, doing this kind of indexing, depending on how many dimensions your arrays have, will take some practicing here. So best to just experiment, create some arrays and start playing around. What if we did something like this? You'd get an error because there's too many indices. The reason why we can only do 3 is because of A3's shape. There we go, 2, 3, 3. Let's try one more. We'll create A4 equals random.rand. Oh no, we need NumPy at the front here. Random.randint. We'll do 10. And this time we'll make it a 4-dimensional array. 2, 3, 4, 5. We want to see it. Shift and enter. Size is not defined. Oh, we keep forgetting to push equals here. That's all right. You'll make some errors too when you're learning to code here. Okay. So A4, we've got a fair few numbers here. We can scroll right down. So if we did A4.shape and then A4.ndim, the shape is 2, 3, 4, 5. We kind of knew that. So 2 by 3 by 4 by 5. Yep. And the dimensions is 4. So this is a 4-dimensional array. Remember, n dimensions can go up to any number you can imagine. So how would we get only the first 4 numbers of this vector here? Let's have a look at this size. So NumPy displays arrays from the outside integer inwards. So let's have a look at this. This might be a bit hard to understand, but with some practice, you'll start to see. So we got 5 here. So the furthest element on the right, the furthest of the shape, gets displayed on the innermost section. So 5, there's 5 numbers here. And then 4, the next section is this section here. So there's 1, 2, 3, 4. Yeah. And then 3. So there should be 3, 1, 2, 3. Yep. So 1, 2, 3. And then 2. So there should be 2 in the largest, so the outermost brackets. So this is 3, and this is 3 here. So there's 2 there. Remember, visualizing these is very hard to understand when you first begin. So if you're having some trouble, try to create some random arrays with different shapes, and then start to count backwards from the outermost number on the innermost displayed array. But let's see, how would we get the first 4 numbers of the innermost array? So that's the innermost here, number 5. So what we could do is slice these first 3 dimensions and then slice this one. We only want the first 4. So let's try that. A4, slice all of dimension 1, slice all of dimension 2, all of dimension 3, but only up to the first 4 numbers of dimension 4. Shift and enter. Wonderful. So that only gives us the first 4 numbers of the innermost dimension. And if we got rid of that to 3, that to 2, there we go. We can start to see how we can really slice and dice our arrays and matrices to give us back any kind of numbers that we might want to see. All right, now we've seen a few different ways to create arrays. We've seen a few different ways to index them and view them. And remember, I'm using the term array and matrix independently. You can use them independently yourself. What we're going to do next is figure out how to manipulate and compare different arrays, which is the crux of what machine learning does to find patterns in numbers. So have some practice, take a little break, try out a bit of slicing, create your own array, and see different ways of viewing it, and I'll see you in the next video. All right. So in the previous few videos, we've had a look at different ways of creating NumPy arrays. We've seen how we can view them. Now let's figure out the fun part. Let's figure out how we can manipulate and compare our different arrays. This is where the crux of machine learning happens, right? It's manipulating, performing calculations, finding patterns in arrays of different numbers. So let's start it off. We'll put in another heading because we're keeping our notebooks nice and neat. Manipulating and comparing. Have I spelt it right? I usually get typos in these headings. Manipulating and comparing arrays. Beautiful. We're going to put a little subheading here because, like pandas with NumPy, if you can think of a way of manipulating numbers, you can probably do it. So the first one we're going to look at is arithmetic. There we go. Lucky my coding is a little bit better than my spelling ability. But arithmetic is a fancy word for basic math equations. So let's have a look. We'll start off by checking out our A1 array. We created this earlier. A1, wonderful. We'll create another one called ones. Actually, we've already got ones. Yep, beautiful. But if you wanted to recreate it, we'll go np.ones3, just to make sure we know what it looks like. Ones. Wonderful. Okay, first one we're going to have a look at is nice and simple, plus. So what do you think this will do if we go A1, which is our array here, plus ones? Well, let's not talk about it, Daniel. Let's run the code. Beautiful. A1 plus 1s. So we've got 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 1 equals 4. Excellent. So all this has done has just added together the different elements in the same position of both arrays. So the 0th position, 1 plus 1 equals 2. The first position, 2 plus 1 equals 3. And the second position is 3 plus 1 equals 4. All right, well, let's keep going. Let's see a few more options. A1 minus 1s. Can you guess what will happen here? 0, 1, 2. So all it's done is it's subtracted 1s from A1. Let's push forward. Let's try and multiply. A1 times 1s. Yeah, well, that makes sense because our 1s array is just all 1s and it's just times A1 by 1. 1 times 1 is 1. 1 times 2 is 2, and so on. Let's bring in another array. A2, here we go. Now this will be interesting. If we multiply A1 by A2, what's going to happen? Let's see. Let's work through this. So we've got 1. Let's get up A1 again so we can see everything in one place. A1. 1 times 1 is 1. 2 times 2 is 4. 3 times 3.3 is 9.9. That makes sense. But what about this second row here? Let's see if we can figure this out by looking at it. 1 is 4. 4. 2 times 5 is 10. Yep. 3 times 6.5 is 19.5. Let's use Python to help us out for that. 6.5 is 19.5. We can get rid of this cell. We don't want that. Actually, never use a toolbar. Escape X to get rid of that. So what this has done is it's taken A1, these three numbers here, multiplied it by this row, put it in here, and then done the same thing again with A1 and multiplied it by this row. That's interesting. Let's have a look at our other array first, A3. Let's combine these two, A2 and A3. A2 times A3. Operands could not be broadcast together with shapes 2, 3, 2, 3, 3. Operands could not be broadcast together. That's interesting. Well, remember right at the start, at the concept video where we talked about where NumPy is fast because it vectorizes code through a technique called broadcasting. Well, this is what's happening here. But to be that fast, broadcasting has a few rules. So let's look that up. NumPy broadcasting. There we go. We're going to go to the documentation, broadcasting NumPy. Click on that. The term broadcasting describes how NumPy treats arrays with different shapes during arithmetic operations, which is exactly what we're doing. We're trying to use some arithmetic on arrays with different shapes. So there's A3 and there's A2. They've got different shapes, and that's what the error is coming up. So let's have a look here. Subject to certain constraints, the smaller array is broadcast across the larger array so they have compatible shapes. Well, that explains what's happened up here with A1 times A2. The smaller array is broadcast across the larger array so they have compatible shapes. That makes sense because we've got here, this is a smaller array. It's been broadcast across this row and then across this row so that the output has a compatible shape of the larger array. Okay, we'll keep going. There's some examples here. So these are two arrays multiplied. They've got the same shape. 1, 2, 3, 2, 2, 2. A times B is 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. That makes sense. And then broadcasting rule relaxes this constraint when the array shape meets certain constraints. Okay, so this is good. This is the kind of workflow you want to start getting into, right? Is if you come across an error like this, and you will all the time, one of these mismatched shapes errors, like different shapes that are incompatible with each other, a value error, these are going to come up all the time in machine learning. And part of being a data scientist or a machine learning engineer is reading documentation like we're doing now and trying to figure out how to fix our problem. So general broadcasting rules, okay. When operating on two arrays, NumPy compares their shapes element-wise. It starts with the trailing dimensions and works its way forward. Two dimensions are compatible when they are equal or one of them is 1. Now, to save a little bit of time, instead of going through the entire documentation, I'll leave that for you. I want you to have a think about, try and figure out a way, how would we get these two to be of compatibility? How would we fulfill this broadcasting need? So what you may want to look into is, how can you reshape A2 to be compatible with A3? So that might be looking at search, put in another comment here, how to reshape NumPy array. So check out the broadcasting documentation along with searching something like this, and then figure out how to make these two shapes align. If you can't, that's entirely fine, right? This takes a bit of practice, but we're going to see how to do it in a future video. Right now, we're going to continue with our arithmetic just to finish things off. So where were we? We've done multiplication. Let's try A1 divided by 1s. So this little slash is for divided by. And you can probably predict what's going to happen here. Beautiful, it works fine because our arrays are similar shapes. Okay, let's try A2. Let's try some floor division. A2 divided by A1, wonderful. But we'll see what non-floor division works here. There we go. So floor division, what this means, if you do 2 slashes, you might have seen this in Python. If not, that's fine. Floor division removes the decimals. So you can see here, it rounds it down. Rounds down. So 1.0, 1.0, 1.0, 1.1, but that's been rounded down to 1. 2.166667 has been rounded down to 2. Let's keep going. What have we missed out on? Let's go square. A2 square 2. This is a power, so to the power of. So everything in here is going to be to the power of 2. So if we look at A2 on its own, it's going to be 1 times 1, 2 times 2 is 4, 1 times 1 is 1, 3.3 times 3.3 is 10.89. We'll confirm that with Python. Wonderful, 10.89, that's just filled it in there and rounded it off. Actually, NumPy has a square you can use with this. So all of these functions that you see here, that we've gone through, arithmetic, floor division, etc., NumPy has the equivalent here. Now, which one should you use? Well, it's going to depend on what your workflow is best at. So if you want to use the math symbol operations, you can use that, or if you want to use square, or you can even go np.add. You're going to go shift tab to figure out what it does. Let's figure out here, docstring adds arguments element-wise. So let's try that, A1, 1s. Same as just doing A1 plus 1s. Wonderful. We've got a couple more. A1 modulo. This is going to show us the remainders. So A1 divided by 2. Let's see where that goes. A1 divided by 2. Let's go NumPy modulo. Mod. There we go. Return element-wise remainder of division. Wonderful. So this is, again, I'm trying to exemplify the kind of workflow you go towards. If you're not sure what something does, you can always look up the documentation and have a look. That's what we did with broadcasting. We've just done that with modulo. If we divided every element in A1 modulo 2, it's going to show us the remainder that's left over. So let's do A2 modulo 2. So this is just showing us the remainder of what's left after we've divided everything by 2. And if you wanted the exponential, if you're not sure what this is, don't worry for now. It's just to highlight the kind of arithmetic that you can do in NumPy. This is going to take the exponential of everything in an array. And if you want the log, you might see this come up in future projects of an array. You can use np.log. So that was a bit of a whirlwind tour of some of the arithmetic functions that you can do in NumPy. Remember, if you can imagine it, you can probably do it. This is only just scratching the surface. So before next video, have a practice around creating some of your own arrays and then using some of these arithmetic functions on them. Remember, if in doubt, run the code. If you're not sure what something does, have a look at the NumPy documentation, see if you can figure it out. I'll see you in the next video. We're going to cover a little topic called aggregation, but we'll save that for the next video. See you soon. Welcome back. In the last video, we learned a few little arithmetic tricks, and we learned that arithmetic is a fancy word for mathematical operations that we can do on NumPy arrays. And so now we're going to learn a bit more about manipulating NumPy arrays through aggregation. Now, aggregation is another one of those fancy words. Let's Google it. Define aggregation. The formation of a number of things into a cluster. Yeah, that's kind of what we're going to do. So aggregation, performing the same operation on a number of things. And in our case, the number of things is our NumPy array. So let's have a look. You might be familiar with the sum method, so .sum or Python sum. So let's make a list. Listy list equals 1, 2, 3. Nice and simple. And we'll go type listy list. Listy list is not defined. Of course, we're making typos. There we go. Type Python list. So if we wanted to get the total of listy list, we could type in this. Sum listy list. Now that's a Python function right there, sum. But NumPy has its own version of these. So let's go back to our A1 array, which is a lot more trusty. Well, not a lot more, but it's just a different type to listy list, even though it contains the same information. It's in a type NumPy ND array. So let's have a look. What can we do with A1? We can call sum on it, and we get 6. We can also call np.sum on A1. We get 6 as well. Okay, now why would there be different functions here? And what is the main difference between these two? It can get confusing having two different ways to perform the same aggregation on a set of data. And remember, aggregation just performing the same operation on a number of things. Sum is just an aggregation to add up all the elements of a certain array or list. Now, the little tidbit you can use here is of which sum you should use, whether it be Python sum or np.sum, is use Python's methods on Python data types and use NumPy's methods on NumPy arrays. So this is sum. Actually, we might do this one in Markdown, so that's a bit easier to read. We don't want heading 1. We'll put this in code. So this is our tidbit, np.sum. There we go. Now let's see this in action. So we're going to create a massive NumPy array. Okay, massive array. This will really demonstrate the power of how fast NumPy can be. Remember how we talked about right at the start? We'll create a massive array with 100,000 different elements. This won't be too uncommon for machine learning problems. So there we go, .size 100,000. Let's just view, just so we can see what it looks like. Massive array. Let's view the first 100 elements. There we go. All random numbers, great. We might reduce that to 10 so we have a bit more space. Wonderful. Now we're going to use one of Jupyter Notebooks or Python's magic functions remember, a magic function has a little percentage sign at the start of it. We got time it. And this is going to time how long a particular line of code takes to run. We'll try Python sum. So sum across massive array. We'll just put a little comment here. So Python sum, and then time it. We want NumPy's sum, massive array. And we'll put a little comment here, NumPy's sum. So let's run this and see what happens. Now it might take a little while because it's adding up 100,000 different numbers. So what have we got here? Well, the first line is going to be dedicated towards this line here. And the second line is going to be dedicated towards NumPy sum. So the first line, to sum over using Python sum across 100,000 different numbers, took 17.9 milliseconds per loop. plus or minus 2.94 milliseconds, 10 loops. But NumPy's sum, np.sum, put that there, np.sum, took 34 micro, this little symbol here is mu for microseconds. So let's convert that. We want microseconds to milliseconds. Equals 1 microsecond equals 0.001 milliseconds. So let's convert, this is milliseconds, we want to convert that to microseconds. 17.9 milliseconds actually to microseconds. There we go. So 17.9 milliseconds equals 17,900 microseconds. My goodness. So 17,900 divided by 34 equals 526. So that means NumPy's np.sum is 526 times faster than Python's sum. So going forward, remember the tidbit here. If you're working with NumPy data, use NumPy methods. But if you're working with Python data types, use Python methods. Because going back to the start, NumPy has been optimized to perform numerical calculations. So whenever you want to perform numerical calculations, always remember to use the NumPy version of an aggregation function. And speaking of aggregation functions, let's have a look at a few more. We'll go A2, we'll have a look at our second array that we created. There's our trusty two-dimensional array from before. Let's find the mean of this. So we go np.mean, A2, 3.633, beautiful. Now the mean would be if we added these up, 1 plus 2 plus 3.3 plus 4 plus 5 plus 6.5, then divided by the total number of items, so 6. We won't do that, but that's how you find the mean. If we wanted the maximum, you can use np.max. If we wanted the minimum, we can do np.min. If we wanted the standard deviation, we can do std for standard deviation. Remember, we can always press Shift-Tab, compute the standard deviation along the specified axis. If we pass no axis, it's going to do it over the entire array, which is what we want. Wonderful. And if we want the variance, we can do np.var A2. Wonderful. Shift-Tab, compute the variance along the specified axis. And now you might be saying, Daniel, what the hell is a standard deviation and what the hell is a variance? Well, variance, let's put a little comment here. What you need to remember is the variance equals the measure of the average degree to which each number is different to the mean. So we want higher variance equals wider range of numbers. Lower variance equals lower range of numbers. Beautiful. And now the standard deviation, the formal definition is standard deviation equals, standard deviation is a measure of how spread out a group of numbers is from the mean. The standard deviation is actually just the square root of the variance. So let's try this out. So we got np, there's another aggregation function, square root of np.var A2 should be equal to the standard deviation. So let's write this down. Standard deviation equals square root of variance. Shift and enter. There we go. These two numbers are the same. Now, if you'd like to look into a bit more of the math behind the standard deviation and the variance, I'll leave some resources in the resources section for you. Otherwise, in the next video, we'll see a bit more of an example of these two in practice. They're an important concept to know going forward in any type of data science or machine learning or statistical work. So let's take a quick break, play around with some aggregation functions that you've seen on some of the arrays we've made, or create your own, and I'll see you in a second. Welcome back. In the last video, we looked at some aggregation functions with using NumPy, such as getting the sum of all the elements in an array. We saw how much faster NumPy's code is to pure Python code when working on NumPy data types. So always use NumPy aggregation functions on NumPy arrays. And then we left off with a brief introduction to standard deviation and variance. Now, the main thing to remember about these two metrics is, in a word, they're just the measures of the spread of data. But let's not talk about it. Let's always focus on running code and seeing practical examples. So that's what we're going to do in this video. So we'll go demo of and var, standard deviation. STD is short for standard deviation. Var is short for variance. So we'll create high var array equals MP array, 1, 100, 200, 300, 4,000, 5,000. Wonderful. Low var array equals MP array. Maybe we'll make this one nice and simple, 2, 4, 6, 8, 10. There we go. Now, before we even run any code, have a look at the numbers in these arrays. Imagine these are actual data. What would you infer from just looking at these numbers? So this one starts from 1, goes to 100, 200, 300, then jumps to 4,000, finishes on 5,000. And this one kind of just goes 2, 4, 6, 8, 10. So first of all, you might look at the difference between the two maximums. That's what I kind of looked at. So this one goes from 1 to 5,000. This one goes from 2 to 10. So if we looked at this, we might say that these numbers, to me, these are more spread out, whereas these are pretty close together, and the maximum distance is only 8, and they have the same step in between each one. Whereas this kind of varies. It goes up by 100 at a time, and then up by a few thousand, and then up by 1,000 to finish off. But let's put it into practice. Let's run the code. Let's see what's going on. So Shift Enter. Let's find the variance of both of them. High var. And we can press tab for autocomplete. MP var. We want tab for autocomplete. Oh no. We need to actually type the start of a variable. That would be helpful. Beautiful. We'll hit Shift and Enter. Now this is an absolutely massive number here. And this is not too big. Well, we're not going to look at the mathematics behind these two. What's more important is the concept here. And the variance, if we go up here, remember, variance equals a measure of the average degree to which each number is different to the mean. Higher variance equals wider range of numbers. Yep. Lower variance equals lower range of numbers. And that makes sense with these two arrays. This array here, high var array, has very high variance. Whereas low array, because the numbers are close together, it has a lower variance. So let's have a look. Let's do standard deviation, STD. We want high var array, and we also want the low var array. We want standard deviation. Before we do this, what do you think the standard deviation is here? Is it going to come out similar to what this looks like? Well, let's have a look. There we go. And that makes sense. The standard deviation is higher for the high variance array than for the low variance array. And what is standard deviation? A measure of how spread out a group of numbers is from the mean. Okay, they've both got mean in their definition, so let's have a look. Let's find the mean. Dot high var array, and we want NP mean low var array. Higher var is not defined. This is why we should use tab autocomplete. So what this is saying is the standard deviation, this number here is the average distance a number is away from the mean. So if the mean is 1,600, that means on average, any other number in this array, in high var array, is 2,072 away from the next number. The same goes for the low var array. Any number in the low var array is on average 2.8 away from the mean. So that means 10. This number is, although it's 4 away from 6, because the mean is 6, 8 is closer to 6. So that's what brings the average down. All right, Now, let's check out the spread. Remember, that's the main crux of standard deviation and variance, is just the spread of numbers, how they appear. Let's plot them. So we can do that by importing matplotlib. We're going to have a look at matplotlib in a future section, so don't worry too much if you're not sure what's going on here. Matplotlib.pyplot as plt. That's what we want. Yep. Plot.hist. So this is a histogram. Hi, we just want that. Tab autocomplete. If in doubt, tab autocomplete. See what comes up. Shift enter. No module name, matplot. Oh, we got that wrong. Matplotlib. There we go. Okay, so there we got the high var array. Now let's do the same for the low var array. Plot hist low var array. And we want plot.show. Wonderful. So now we can see visually, if you couldn't see it from these numbers in the number line here, now visually we can kind of see the spread of the numbers of high var array is a lot bigger, so there's a lot more white space here. A lot of the numbers appear towards 0, and only 2 of the samples appear up here. Whereas in our low var array, the spread is kind of similar across the whole thing because there's gaps of 2 between each data point. And the maximum distance here is only 8. All right, so that's standard deviation and variance in a conceptual level. Now remember, if you do want the mathematics behind this, how these two values here, the standard deviation and the variance, are calculated, I'll leave some extra resources, but just remember the main takeaway from this is that standard deviation and variance are measures of spread of data. Now, with that being said, we finished up some of the most common aggregation functions you'll see in NumPy. Let's get into the next section where we can check out some more ways of manipulating arrays. Okay, now we've seen a few different ways to manipulate arrays, but most of the ways we've worked with have been arithmetic or aggregation, so kind of performing calculations on NumPy arrays. Now, what if you needed to change the shape of your NumPy array? Now, why would you need to change the shape of a NumPy array? Well, remember, a lot of machine learning is lining up your inputs into a machine learning algorithm and making sure that they come out with the right output. One of those ways of lining up inputs is making sure your data or your list of numbers or your array of numbers is in the right shape. So let's have a look at how to do that in NumPy. So we'll go reshaping and transposing. This is this section. Nice little heading there. So let's have a look. A2 array, beautiful. Let's figure out what shape it is. 2 by 3, yep, that makes sense. Now, remember before in a previous video we tried to multiply A2 by A3. Let's visualize A3 so we can see it again. A3, there we go. Let's check out the shape. A3.shape. Okay. Now what's going to happen if we try to multiply these? Operands could not be broadcast together with shapes 2, 3 or 2, 3, 3. Well, the beautiful thing about NumPy arrays is that they can be reshaped or transposed. Let's have a look at reshape first. So what does reshape do? Reshape is a method you can call on any array. So if we type in here, .reshape, shift tab, reshape docstring, returns an array containing the same data with a new shape. Beautiful. There we go, we've got some more information there. Let's see what it requires. Shape. So one of the rules of broadcasting, if we look up broadcasting one more time, one of the rules of broadcasting is here. General broadcasting rules. When operating on two arrays, NumPy compares their shapes element-wise. It starts with the trailing dimensions and works its way forward. Two dimensions are compatible when they are equal or one of them is 1. So what this means is that if the shapes of two arrays are equal, the multiplication can happen. But if they're not equal, one of them has to be 1. So that's what we're going to do here. We're going to reshape the A2 array from its shape 2, 3, incompatible here, and we're going to change one of these dimensions. We're going to add a dimension actually. So reshape 2, 3, 1. Let's see what happens. Ah, okay, so it's shuffled our array around a bit. Let's print the shape here. So see our A2, we've used the reshape method, passed it a different shape. So now we've added another dimension here. And now its shape is 2, 3, 1. We'll check A3's shape. Okay, 2, 3, 3. So if we refer back to the rules of broadcasting, are the dimensions equal? No. Is one of them 1? Yes. So let's try this. A2, we'll make a variable, A2 reshape equals A2.reshape, 2, 3, 1. Beautiful. So we'll have a look at this, A2 reshape. There's our reshaped A2. A2 reshape times A3. There we go. Beautiful. So that is the benefit of reshape. Now this is only a small example here. Before they were incompatible, but because we reshaped it, we reshaped A2 to be within the broadcasting rules of NumPy, we could then use the multiplier function across these two arrays. Now if this concept is kind of strange to begin with, that's perfectly fine, and it will be. It will take a fair bit of practice to figure out how to use reshape properly. But what the important takeaway here is that just because your NumPy array comes in a certain shape, like it begins like this, doesn't mean it has to stay in that shape. So this reshaped version of A2 still contains the same information as the original A2, it's just in a different shape. So this is one of the problems you'll come across in many different machine learning problems, is making sure that the data that you're trying to find patterns within is the same shape. So the machine learning algorithm can run over it, like this broadcasting operation, as quickly as possible. And if they aren't the same shape, you'll often get back errors like this, which say the data you're trying to find patterns in isn't the same shape. So that's when you have to figure out how to use something like reshape to turn them into the same shape so that they're compatible with each other. Now, there's one more thing, which is transpose. Now, what transpose is, let's have a look at it first. Let's put a little comment here so we know what's happening. Transpose. A2, actually, we might leave it here, A2.t, so we can see what's changed here. Let's get A2 back up. A2's there. Transpose. What's changed? Let's go .shape. 3, 2. Okay, now if we go here, A2.shape. So what a transpose does, it switches the axes. So now, A2's shape was 2, 3, but if we call transpose, and now T is for transpose, it's going to swap the axes around. That's where we can see that now 1, 2, 3.3 is down here in the column, and 4, 5, 6.5 is on this column. So what it's done is essentially just swapped the rows and columns. Now you can do this on a larger array as well. Let's view A3, A3.shape, 2, 3, 3. So if we call A3.t, it's going to swap these axes around. So if let's see, A3.t.shape. So now we've essentially flipped it. So now this dimension, so 2 is right at the end, and 3 and 3 have swapped to the front. The important difference here between transpose and reshape is that transpose just flips the axes around, and reshape, you can create your own custom shapes. So for example, we reshaped A2 to be compatible with our broadcasting rules. So have a practice reshaping some of your arrays, and I'll see you in the next video. Now that we've covered reshaping and transposing, you might be thinking, when would we ever want to use a transpose? It just flips the axes around. When is that useful? Well, that's what we're going to cover in this video. And one of the main use cases for transposing a matrix is the dot product. You might be thinking now, dot product? What the hell is a dot product? Well, let's do what we do. Dot product NumPy. Let's have a research, because this is what we're practicing. Here we go, NumPy dot product of two arrays. Oh, that's not very helpful. Sometimes you'll get that in the docs. It'll give you a very brief explanation of what happens. Specifically, if both A and B are 1D arrays, it is the inner product of vectors. Okay, there's a few text instructions here of what dot product actually is, but let's focus on the code. We'll go back to our notebook. We'll write some code first, and then we'll have a little look into what the dot product actually does. The thing you need to remember with the dot product, it's just another way of finding patterns between two different sets of numbers. So let's start off with a random seed. We'll create two more matrices that we can use for an example. We want this one to be rand int. Let's make it of size 5 and 3. And we want mat2. Beautiful. We'll just make it the same thing. Random.randint 10 size equals 5, 3. And now we've seen randint before. Do you know what these two lines of code will do? So let's have a look. As a reminder, we can do Shift Tab. Return random integers from low to high. Beautiful. Let's see these in action. Mat1. Wonderful. Mat2. Even more wonderful. And then we also want to see, we already know the shape, but let's just do it anyway. So we've got the shapes here. Mat2.shape. Wonderful. So in a previous video, we've seen a few different ways of performing arithmetic on matrices like this. One of the ways that we did was multiplication. So we go mat1 times mat2. Let's bring these down so we can see them, because I want to stay nice and zoomed in to keep the code big. There we go, mat1, mat2. Wonderful. This array down here is just going to be the combination of these two multiplied element-wise. 5 times 6 is 30, 0 times 7 is 0. But this is, I said a little tricky word before, element-wise multiplication. There's a few different names for this, but it's mostly called element-wise. Hadamard product. That's how you spell it, I believe. Let's have a look. Hadamard product. NumPy. That's what we're after. How to get element-wise. Yeah, np.multiply, which is the same as using this little star symbol. So that's element-wise multiplication. Another form of multiplication or product between two matrices is the dot product. So let's have a look at that. Dot product. If we go back actually to our documentation, the formula for doing a dot product is np dot. You could use NumPy dot, but we've imported NumPy as np. So we're going to do np dot, we want to form mat1, mat2, which is just our two matrices that we made. So let's run this. Oh, that didn't work. Damn it. Our value error, shapes 5, 3, 5, 3 not aligned. 3 dim 1 does not equal 5. Okay, we go back up to see the shapes of our matrices. They're both of shape 5, 3, 5, 3. And this is saying shapes 5, 3 and 5, 3 not aligned. Well, the difference between dot product and element-wise. So we've seen element-wise before. It's relatively simple. We've got A times E goes into this top left square. A times F, oh no, sorry, B times F. I just said it's simple and here I am messing it up. B times F. But if we kept going through that, we'd eventually end up with this matrix. But the dot product is a little bit different. Now, we've got, say, a 3 by 3 matrix here, a 3 by 2 matrix here, and we're calling dot on this one with this one. And now, what is going on here? The resulting matrix is going to be 3 by 2. And we have A times J, okay, following along with that. But then we have B times L plus, okay. Then we have C times N. All right, so it's got the top row here multiplied by the first column and adding up the total. And now, let's look at a little bit more of a colorful demonstration of the dot product. So here we've got the letters matrix. If we go back here, got the same one as here. Now we've got some color added. This is the top row of the matrix on the left multiplied by the column of the matrix on the right equals this top left square. And then if we kept going through, we would eventually get this resulting matrix here. But there's a couple of rules with a dot product. The numbers on the inside must match. So for a dot product to happen between two matrices, their dimensions, if you put them side by side, so this 3 matches this 3. So this matrix here has 3 rows, and so does this one. And now the resulting matrix is the size of the outside numbers. So the dimensions here are 3 by 2 of this resulting matrix, because the outside numbers of these two matrices are 3 and 2. Okay, so we've got that. For a dot product to happen, the inside numbers must match. Now let's have a look with some numbers that have actually been filled in. We've got 5, 0, 3, 4, 6, 8, and we're calling dot between this matrix and this one. So we've got 5, it's going to come over here, be multiplied by 4. That equals 20. Yep, we've got that. 5, 4. This is A times J. Now we've got 0 times 6. 0 times 6. This is B times L. Yep, we've got that. We're adding that up. Then we've got 3 times 8. This is C times N. All right, and that's 24. And if we added these three numbers together, so we're going to go A times J plus B times L plus C times N. Yep, beautiful. We get 44. And that's going to fill the top left square of our resulting array. Now, if we went through these two matrices with numbers full and followed the same steps that we've got in this letters matrix, we would end up with something like this. But this is a static demonstration. So let's check out this little beautiful resource here, which is an interactive demo. So this is matrix multiplication.xyz. This is called the waterfall technique, what this demonstration is going to do. And you can change these numbers here to be something similar to maybe what we've got here, or just to view the process of what's happening. So if we click multiply, it's going to take the matrix that was on the right and put it on top. This is where the waterfall process comes in. Now it's going to flow down. So this row 2, 6, 1 used to be here as a column. And if we add these together, multiply them, we get 15 in the top left. What it's done is it's just replicated this step here. We've got the top left. Now if we follow it through, okay, we get the top right and we get the middle left. Then we get the middle right and the bottom left. And then we finally finish up with the bottom right number. So have a play around with this if you check it out. You can keep going through. It takes a little bit of practice to understand the dot product. Let's go back to our notebook. And now that we know a little bit more about the dot product, we know the rules. The numbers on the inside must match, and the new size of the resulting matrix is 3 by 2 because it takes the outside numbers. How would we make this work with our matrix 1 and matrix 2 if their internal shapes are 5 and 3 and 5 and 3? Well, maybe we could use a transpose. Let's try that out. Transpose mat1. Because what does a transpose do? It flips the axes around. So let's go mat1.t. What does that look like? Okay. Might look at that and see maybe it'll work, but let's really confirm it. mat1.t.shape. 3, 5. Is that what we need? Yeah. We need to flip it around. So if we have mat2.shape. Beautiful. So now the inside shapes, if we were to transpose mat1, are matching. So let's do this. Or actually, before we did np.mat1, mat2. Okay. Maybe we transpose mat2. mat1.shape, mat2.t to stay consistent with what we got above. Let's make mat3 equals np.mat1. And then we want mat2.t. So this should work if our shapes are aligned. Mat3. Beautiful. And now if we have mat3, what is the shape of mat3? Yes, excellent. So now we can see where the transpose might come into play. If we wanted to do a dot product on two matrices where in our first try the shapes were incorrect, we might want to flip the axes. Of course, you could do this with the reshape as well, but this is just a handy example where transpose comes into play for performing something like a dot product. Now we can see the resulting shape of matrix 3 is the same as the outside numbers. Wonderful. Now, when I first came across dot product, it took me a little while to understand how to actually go through it. A great exercise was to write out a matrix by hand and multiply it and figure something out like this, or use the demo at like matrix multiplication.xyz. The main takeaway from the dot product is that it's just another tool in our arsenal to find patterns between two different arrays of numbers, as we've seen before. Now, in the next section, we'll have a look at where the dot product might be used in practice. So have a practice around, create some matrices, transpose them, see if you can do a dot product, and I'll see you in the next video. Welcome back. So hopefully you've had a little bit of play around with the dot product, maybe created your own matrices, tried it out. If not, that's okay, but remember, the best way to learn is to always run the code yourself first. And then again, maybe if you are even doing that, sometimes it's hard to understand like different concepts when you just see numbers on a page. So it's always good to try and back things up with a practical example. So let's have a look at one where the dot product might come into play. So this is my Google Sheet. I'm tracking my nut butter sales for my future nut butter business because my favorite food in the world is almond butter. And now this business, we create 100% almond butter, 100% peanut butter, and 100% cashew butter. And so this is just a simple tracker to track how many jars I've sold on each day. Friday was a massive day because we sold 15 jars of almond butter. Then we've got the prices here of each one. So almond butter is $10, peanut butter is $8, and cashew is a little bit more expensive, so cashew butter is $12 per jar. And now, what my goal here is to figure out this total column, because that's what I want to know is, what days am I making the most money? Monday must have been a slow day. But if we click on this cell here, and we have a look at this, we can see that this formula is relatively the same, well, similar, not exactly the same because there's different letters and numbers, to our dot product formula back on our slide here. So A times J plus B times L plus C times N. And that equals 44. Well, if we come back, we've got B2, which is 2, times B9, which is the price of almond butter, plus C2, the number of jars of peanut butter, times the price of peanut butter. And then we've done the same for cashew butter. And now we get the total. So this is an example of where the dot product can come into play, is where we want to reduce the numbers we have here and find out the pattern between them. So I've got numbers of jars being sold here and the prices, and the total price is the pattern between these two. And I want to emphasize the fact that this can be replicated in pure NumPy and Pandas, not just in an Excel spreadsheet. So let's put this to the test. What we're going to do is create a little title here. Dot product, example, nut butter sales. And we're going to recreate this example, this whole set here from scratch using nothing but NumPy arrays and pandas. So let's do that. NumPy, we'll set a random seed so the random numbers we create are similar to the ones here, hopefully. That's the idea of random seed. Then we have sales amounts. We got np.random.randint. We want it up to 20 is a good amount of sales. If I'm selling more than 20 jars, I need to step up my supply chain. Sales amounts. So this will be, we'll put a little comment here, number of jars sold. There we go. 12, 15, 0, 3, 3, 7. And now we want to create a data frame. Create weekly sales data frame. So this is to put it into pandas so it looks a bit more presentable than just a NumPy array. So let's do that. Weekly sales equals pd.dataframe. We want to add our array, sales amounts, which we've just created up here. And then for the indexes, we'll come back our indexes are going to be days of the week. So let's do that. Index mon, choose, and write out the days of the week here. Wed, little abbreviations will do. And fry, wonderful. And then our columns, we're going to fix this up. We've got almond butter, peanut butter, cashew butter. Wonderful. Columns equals almond butter, peanut butter. It might seem a bit tedious to type this out. We could always export this as a CSV and import it in Pandas, but it's always good practice to build your own things from scratch. That way you really start to understand what's happening. Let's have a look at weekly sales. Okay, wonderful. So the numbers are a bit different here from what's going on there, but the process is going to be the same. So now we've just recreated this section without the total column in a Pandas data frame. Wonderful. So now we want the prices. So we want create the prices array. We'll keep this the same. So what are the numbers? 10, 8, 12. So we can do that with a simple NumPy array. mp.array. We want 10, 8, 12. Wonderful. Let's have a look. So there's a simple NumPy array. Now we want to put that into a data frame as well. Create butter prices data frame. We have butter prices equals pd.dataframe prices. We want here index equals, so the index is just this column here. So we want price, wonderful, price. And then we want columns is the same as above. I might just copy this. Usually we want to write it out, but to save a little bit of time of typing this out, we've got the same columns. Because if we go here, same columns. Wonderful. Put that in there. Oh, we've got an extra bracket. There we go. Now let's have a look at our butter prices data frame. Error. Wrong number of items passed. One placement implies 3. If we come back, shape of past values is 3, 1. Indices imply 1, 3. Now that's our problem here. So this is a weird thing in NumPy where we go prices.shape, it equals 3 something. But what Pandas is expecting is 3 columns and 1 row. But this is 3 rows, 1 column. We want to reshape this to be 1, 3. There we go. Wonderful. So what we've done is we've recreated this little section in Pandas. Beautiful. So now, how do we do this? We need to do a dot product of sorts on this and this. Okay, and then add it to this and this and then this and this and add it up and get that. All right. So let's try. So let's just do, what have we have here? We've got, where's our total sales? Sales amounts. Yep. And prices. Let's make total sales equals prices, which is, we'll have a look at prices again. Prices dot sales amounts. What happens here? Not aligned. We want to have a look at our sales amounts actually. And this is saying that the shapes aren't aligned. So we can see that the sales amounts shape is 5, 3, and the prices shape is 3, 0. Okay, that makes sense. We've seen this before. We've seen the shapes of dot products not fitting together. The shapes aren't aligned. We need to transpose. Shapes aren't aligned. Let's transpose. If we go total sales, which one do we have to transpose? Maybe if we try to transpose sales amounts. Total sales equals prices dot sales amounts dot t. Oh, there we go. That worked. Total sales. Wonderful. Okay, now I've got something that looks kind of like this. Again, it's with different numbers, but now we've got some total sales. Okay, so how would we get this as a column on the very right-hand side? Let's have a think. let's try something. Let's just, if in doubt, run the code. Create daily sales. Maybe I create the same thing as here, but within a pandas data frame, so we can kind of just add the two data frames together. So let's butter prices, which is this. Yep. What else do we want? We want weekly sales. Yep. So we want these two. We want to combine these two. So we want shape. Maybe we get weekly sales dot shape as well. Okay. Ah, there we go. So now this is starting to look familiar. Maybe if we flip weekly sales, which is our data frame, flip that, transpose that, and then dot product of those two. Because then if we flip these two, right, there'll be 3 on the inside, and the 3s will line up. Daily sales equals, we should be able to do a dot product. Dot weekly sales dot t. So that's a transpose there. Oh, that might have worked because, let me prove it to you. Weekly sales dot t dot shape. Excellent. Here we go. We might be cooking with gas here. Beautiful. So this should be the totals. Now, how do we get this onto the right-hand side of our data frame? We want to put this on there here because that's what we're recreating, right? We're putting this total on there. Okay. We can do this. How do we create a new column in pandas? We go weekly sales. This is our data frame here. We want weekly sales total. Maybe we'll put a little $sign there so we know what's going on here, equals daily sales. Daily sales is this little pandas data frame here. We're going to go type daily sales data frame, and we want to add that data frame as a new column on the back end of our data frame here. So let's see what happens when we do this. Weekly sales. Oh, that didn't work. What's the error here? Key error total. Total. Maybe the column title doesn't work. Wrong number of items passed, 5. Placement implies 1. Ah, because we're getting into another shape error. So this is a row, but we want that in column form. So maybe we have to transpose this. Okay, let's do shape. And then we want the shape of our weekly sales data frame. Ah, okay, so we want our daily sales to have the same number of rows as our weekly sales, and then we should be able to append it. Okay, we'll put a note in here. Doesn't work, not the right shape, but what we can do is come down, we'll make a new cell. There we go, weekly sales total. That's a terrible way of spelling total, Daniel. Weekly sales total equals daily sales dot t for transpose. And now this, hopefully, beautiful. There we go. So now we've just replicated with a few steps in between of shifting shapes and whatnot. We've replicated this column here, figuring out how much I made from each day. Monday was a terrible day, couldn't pay the rent with that money. Well, in this data frame, it's actually a bit better. Wednesday was my biggest day in this one. We've now seen where manipulating the shapes of arrays and performing a dot product can work in practice. So this video was a lot to take in, so I'd go back through and just have a little practice around. Maybe create your own store. Maybe you want to sell your own favorite food product or technology or something like that. Make a prices array here, make a total column, and try to replicate it using NumPy and pandas. And see if you can end up with something like this. That'll be a good practice exercise. Okay, don't forget, try to run the code yourself. If it doesn't work, keep trying, search it up, and I'll see you in the next video. We've seen a fair few different ways of manipulating arrays, but right up the top of this section, we're not going to go right up the top because it's pretty lengthy already. We called it manipulating and comparing arrays. So that's what we're going to cover in this video is comparison operators. We'll make a nice little heading. Comparison operators, beautiful. That's how we spell operators. Change it to Markdown. Now, you might have seen comparison operators in Python. Well, the good news is that in NumPy arrays, you can use those same comparison operators. So let's have a look. Let's get back our trusty A1 and A2 arrays. Wonderful. So let's try it out. We want A1 greater than A2. What's this going to return? It's going to return another array because that's the fundamental data type of NumPy. Basically everything is an array, an ND array. It's going to tell us whether each element in A1 is greater than each element in A2. So you can see 1 is not greater than 1, it's equal to 1. 2 is not greater than 2, it's equal to 2. 3 is not greater than 3.3 because 3.3 is higher. So let's have another look. Let's go A1 greater than or equal to A2. Now we can see we've got some true. So we've got some Boolean data types being returned in this array. So maybe if we go bool array equals that, bool array, we want to see that, and then we want to go type, you know the type, let's see it anyway. Type, it's going to be ND array. And then if we also wanted bool array dot D type, it's going to be data type bool. So this array is full of booleans here. Wonderful. So now we can see again, we got A1. Let's try another comparison of just a simple integer. A1 greater than 5. No. False, false, false. Let's go A1 less than 5. True, true, true. Wonderful. If we want to see if two arrays are equal, we can use the equal then comparison operator. That's a mouthful for me. True, true, true. That makes sense. We go A1 equals A2. Wonderful. We can see that the first two elements, oh, let's go back down so we're not scrolling all the time. A1, another cell here, A2, and we can see, yep, element 0 is true, element 1 is true, and then the rest aren't equal. Okay, now if you wanted to find more of these comparison operators, we've just been through a few, you can try out some of your own. Let's look up the documentation, NumPy comparison operators. Logic functions, yeah, let's have a look at this. All, any, array contents, there's a fair few here. Less, less equal, equal. We can use these symbols here. Okay, so there's a fair few more that we can do, but these are the main ones that you'll need if you ever need to compare arrays. You can use the exact same symbols that you use in Python with NumPy. So that's going to wrap up the manipulating and comparing arrays section. Let's go have a look at the next part. I'll see you in the next video. So we've been through a hell of a lot so far. We've looked at creating arrays, we've looked at viewing arrays, we've looked at manipulating and comparing arrays. Now, number 5, which is if you have an array of numbers, sometimes you might need to sort them. So we'll go sorting arrays, make a nice little heading here. Beautiful. So let's have a look. Have we still got random array? Somewhere we created this. Okay, wonderful. Now, if you wanted to recreate this, how would we do that? So let's go equals np.random. Now this is full of integers, so we want rand int, and we want up to 10, and we'll give it a size of how many? What's the shape of random array? I believe we could tell this by just counting the rows. 3 by 5. So let's see. 3 by 5. Wonderful. 3, 5. So we'll just recreate that if you don't have it. Otherwise, you can just use the one that's saved in memory. We recreate it for completeness. Wonderful. Random array.shape. There we go. So now what if we wanted to sort the numbers in this array? Well, NumPy has a function called np.sort. We're going to check Shift Tab to see what it does. Return a sorted copy of an array. And this is A is the array. Wonderful. So if we pass random array in there, what's it going to do? It's going to sort the numbers on each axis. So if we see this first one here, this first array, 1 is now on the very left. 5 comes after that because it's the second highest, then 7, then 8, then 9. Wonderful. So now let's keep going. NumPy also has a method called argsort, and we're going to see what this says. Returns the indices that would sort an array. So sometimes you might not want to sort the values. Instead, you want to figure out which index has the highest value. So let's do that. We'll pass it random array. Wonderful. Getting a bit confusing here, having all these different arrays. We'll see random array again. So we've got random array here. We're calling argsort on it. So this is going to sort the indexes. So 1 is the lowest, so that's got the 0 number, yep. Then 5 has got 1, yep. And then 7 has got 2. Wonderful. Okay, so this is sorting the indexes for us and telling us what order they would come in. So let's see our trusty array A1. We'll see another example of that. np.argsort, nice and simple. So we can see this is already in order if we use argsort. Okay, so this is the order that the indexes would come in, 0, 1, 2. Makes sense. What if we wanted to find the minimum number? Where the index where the minimum number comes from. We can do argmin. A1 is 0. So the minimum value in A1, argmin, the index it appears at is 0. We can do the same with argmax, where we want the max value of A1. 2. What if we did argmax on our random array? We'll review our random array again. Argmax, random array. We want to know where the maximum number occurs in one of these arrays. So let's see what happens. Let's do a shift tab first, actually. Returns the indices of the maximum values along an axis. Okay. 4. Well, what axis is that on? Well, that doesn't really help us. Let's go axis equals 0. Ah, there we go. So this is going to give us the maximum values along axis equals 0. So this is 1, 1, 1. So index 1 has the maximum value. I think axis 0 is going to be for the rows. Let's figure this out together. Argmax, see, this is where I get confused as well, looking at different arrays and trying to sort them out, axes. What happens here? 4, 1, 1. Okay, so this is going in the columns, I believe. Ah, so this is where we're getting confused. So we have here, this is position 4. This is the highest number. Yep, so axis 0. Then we go on position 1. We have number 9 here. Yep. In the row 3, the highest is 1 here, so 5 is in that. So then on the flip side, we just went down vertically. Now if we go down horizontally, which is what axis 0 is, across here, we have 1 is the highest, and we're looking at these 3 numbers. So yep, position 1, yep. Then we have 1 again, so 0, 1, 2. Yep, that's position 1 there. Then if we go here, we have the max is 4, 0, yep, 0. So that's where it takes a little bit of practice of just typing out commands like this and viewing them and then working it out for yourself. I've been doing this for a while now and I still get confused with different axes of NumPy arrays. So don't fret if you're having trouble going, oh, which axis is this related to? Which is that? Sometimes viewing arrays like this gets a bit confusing until you actually type out a command and then go retrace the steps back through. So what else do we have? Well, I think that'll probably sum it up for sorting arrays. Now, the beautiful thing about NumPy is that all of these functions you've seen can be used across any ND array. So don't worry if it all seems overwhelming that we've been through in terms of manipulating, comparing arrays, sorting arrays. Have a play around, create some of your own arrays and manipulate them, try to sort them, try to do dot products on them and whatnot. I learn the most when I just try to make some things out of numbers, and a practical example really helps. So before we wrap up the NumPy section, let's have a look at a practical example. Okay, now we've got some of the foundations of NumPy down pat, or maybe not, it's all right, you don't have to know everything up by heart for now. Let's look at a little practical example to finish things off. Practical example, NumPy in action. Play the beautiful action music. Beautiful? Wrong word. Let's go intense action music, rock and roll. Now, if we come back here to our Jupyter dashboard, I've got a little folder here called Images, which I've just created. And I've got some photos in here. So the whole premise, remember we talked about it right at the start with NumPy, is in machine learning, you take whatever data you have, you turn it into numbers, You use a machine learning algorithm to find patterns in those numbers. So what if your data happened to be images and you wanted to find out information about those images? I'm going to create a little markdown cell here and import. I've got a panda image that we've used in the pandas section. So we're going to turn our wonderful panda. We can see it there. Look at that. He's stoked. Give it a high five. I'm high-fiving the screen. What we want to do is we want to turn an image into a NumPy array. Because once we've turned this image into a NumPy array, then we can use the functions that we've learned throughout this entire section to find patterns in that. And we can manipulate it a bit. We could pass it into a machine learning algorithm. The world is our oyster when our data is in numbers. So we have here matplotlib. We're going to see matplotlib in another section. Import imread. So this is just a little package within matplotlib called imread, which stands for image read. What this is going to do is imread. We might use our shift tab to figure this out. Oh, is it going to be there? Maybe because we haven't imported it yet. Oh, needs something. That's okay. We want to go shift tab. There we go. Read an image from a file into an array. That is exactly what we want to do. Fname stands for file name, I believe. String or file like the image file to read. Wonderful. Now our panda image is in the file images under panda.png. So we can pass it a string here, panda.png. What we might do is before we even look at it, let's check what type it comes in, panda. Oh, we forgot the images folder. That's all right. Class NumPy ND array. Yes. Now, what does that mean? Well, it means because it's in ND array format, we can use all of the functionality that we've learned about NumPy on this array. So let's have a look at it. Panda. Wow. There's a lot of numbers there. Let's check out some of the attributes of it. Size, panda.shape, panda.ndim. This is pretty big. What's that number? 24,465,000. It's got a lot of dimensions here. It's a three-dimensional array because the three dimensions are color channels. And what this array actually is, let's just view the first 100. So these numbers here, maybe that's even too many. Maybe we want to view the first 5. There we go, first 5. What this has done is a little function, imread, however you want to pronounce it, has taken this picture and then found all of the little pixel values. So if we zoomed right in here, you might not even be able to see a single pixel. That's all right. We zoomed right in here, got the pixels. Those pixels have color values, so red, green, and blue. And that is what is stored in this array. So if we did the same, let's have a look maybe for another image. So we've got imsource. We have another one, images, tab for autocomplete, car photo. This is what I have. Now you can try this with your own image. Beautiful. So what we're going to do is we're going to car equals imread that same images car photo.png. Wonderful. We're going to check it again just for completeness. Type car NumPy array. Beautiful. So now we've turned this car photo into an ND array. Wonderful. Okay, maybe we'll just only see the first section of that. Let's have a look at one more photo. Dog equals imread images. We've seen this dog photo before right at the start. My beautiful puppies. We're going to turn them into numbers. Actually, we want to view it first. So we'll go img source equals images dog photo. Now, if you have a PNG image, this imread function will work with your own. So you could try that. To start using it, you just need to run this from matplotlib import imread. Then you can use this. Remember to use shift tab if you want to figure out what it does. So we'll turn this into markdown. There's my beautiful puppies. That's 7, that's Bella. So we're going to turn the puppies into Can you guess what data type? NumPy array. Wonderful. So we got dog. So now what we could do with this is we've done one of the biggest steps of all machine learning is we turned our data into numbers, specifically a NumPy array. So what a machine learning algorithm would do is because it can't really look at this, us people, we can look at this and go, that's a tree, that's a dog, that's eyes, that's a shelter. But what a machine learning algorithm needs is numbers. And that's what it's got here in the form of a NumPy array. So what it would do is it could take, say this tree is this section of numbers here. Probably not, but let's just imagine it is. What it will do is then go to this image and then look at this section of numbers here and go, oh, okay, those numbers are pretty close to each other. So this item here in this image must be a tree, and this must be some grass. And then same thing in here, this must be some grass, because the pixel values are very close together in both images. So that's going to wrap up the NumPy section. What the important takeaways from this is to remember that we have covered a lot, and you don't need to know all of this off by heart to begin with. It's just I've gone through some of the major concepts and functionality of the NumPy library. The biggest thing is that NumPy handles data types like this, arrays, very, very well. So if you're working with machine learning and you're working with doing mathematical operations, you're trying to find patterns in data, you're probably going to use NumPy. And if you don't understand everything right now, that's okay. There's a lot to take in. Have a break, play around with some of your own images, try and turn them into NumPy arrays, go back through what we've covered, and I'll see you in the next section.